Hi, you are welcome to this 6th lecture session of the course Database Management Systems. In this session, we will discuss relational algebra and then relational calculus, which are formal query languages for relational database management systems or relational data model. First, we will discuss query languages and then formal query languages for relational data model, and then we discuss about introduction to relational algebra. Then we will look into relational operators, set operators, join operators, aggregate functions that are used in relational algebra, and then grouping operators. Then we discuss relational calculus concepts. And in this session, we will have full length discussion about relational algebra and then brief introduction to the relational calculus. And both relational algebra and then calculus are formal query languages for relational data model. Querying means extracting data from the database for the purpose of processing it. Not just storing data into the database is sufficient, and as and when it is required, the end users or the application programs must be able to retrieve or extract the data back from the database with an intention to process it or manipulate it. Every data model has some formal query languages to support specification of data retrieval and then manipulation requests. In our relational data model, it also has formal query languages like relational algebra and then relational calculus. The relational calculus, we have two kinds of relational calculus supported, that is tuple relational calculus and then domain relational calculus. And these formal query languages for relational data model, that is relational algebra and calculus, they have strong mathematical background, and only experts can specify their queries using these formal query languages. Okay, to make it easy for end users or naive users, the database management system vendors, they have come with they will support the commercial query languages, and then most popular commercial query language for relational data model is structured query language, or otherwise it is called as SQL. Simply it is called as SQL. And one more commercial query language known as query by example is also available, but out of these two, SQL is the most popular one. And by default, all nowadays it has become a de facto standard that all commercial database management system vendors, they support the SQL standards. In this particular class, we discuss about the relational algebra and then relational calculus. Relational algebra is a formal query language for relational data model. A basic set of relational model operations constitute the relational algebra. These operations enable the user to specify basic data retrieval requests. The result of a relational algebraic operation is also a new relation. Relation means here we can think about it as a table, and this new relation which may have been formed from one or more relations. And a sequence of relational algebraic operations forms a relational algebraic expression, and whose result is also an relation, and which can be treated for all other purposes. And this new resultant relation can also be used as an operand in other relational algebraic expression or operation. And here in relational algebra, the relations themselves, they become operands. We have operators, and then relations or tables themselves, they become operands. That is why it is called as relational algebra. The relational algebra supports two kinds of operations. First is set theoretic operations, second one is relational operations. In set theoretic operations, we have union, intersection, difference, and then Cartesian product or simply cross product. Under relational operations, we have select operation, project operation, join operation, and then division operation. First, we will see what is a select operation in relational algebra. This operation is to select subset of tuples that satisfy some selection condition. Suppose if there is a relation or relation instance which comprises of some tuples, and then if you want to select only some of the tuples based on some condition satisfying some condition selection criteria, then we can use this selection operation. The symbol used to specify this operation is sigma. This is the symbol used to specify select operation. For example, the general form of select clause is going to be like this in relational algebra. This is the relation on which we are going to apply this operation, and this is the operation, that is select operation, and here as a subscript between this symbol and then this relation we can specify the conditions. It could be one condition or more number of conditions can be there, and which can be joined using logical operators and or. This is the general form of select clause in relational algebra. For example, let us assume that there is an employee relation or employee table which has employee ID, employee name, and then department number, and the name of the relation is employee. Then let us assume that it has some valid tuples. We have, each tuple will have 3 fields or 3 values. Now if we wish to find out the details of employees who are working with department number 4, then we can specify the relational expression like this. It is EMP, that is a relation on which we are going to perform this select operation, and then the select symbol, that is sigma, is used here. As a subscript here we will be specifying the selection condition, that is where DNO is equals to this one, this DNO is equals to 4. That means while executing this, the meaning is at the time of execution it will pick up each tuple and then it will check whether the value under the column DNO is equal to 4 or not. If it is equivalent to 4, all such tuples will satisfy the condition and all such tuples will show up in the result. The above expression, relational algebraic expression, selects all tuples from employee table where the value of the column DNO is 4. And if you carefully observe, this operator, that is the select operator, has only one operand. This is the operator. Normally what we will have, if it is a binary operator, we have operand 1 and then we have operand 2 and then you will have a operator plus or minus, something like that. But in this case, this operation, it is a unary operation. That means it requires only one operand. The operands in relational algebra are nothing but the relations themselves. That is why it is called as relational algebra. And next important operation is the projection operation, where in the case of select operation we have selected only few subset of the tuples available in a relational instance, whereas if we use the project operation we are going to select certain columns. The symbol used to specify this expression or operation is the pi, that is this symbol we will be using to specify this operation. And this is the general form, that is, suppose if I want to project on the name and age and then department number of the employees, let us assume that there is a relation called as employee which has so many fields like employee ID, name, age, department number, address, so on and so forth. And from this particular relation, if we want to project on the name of the employee, age of the employee and then department number, then I can specify the query like this. This is the relational algebraic expression which will give me the name, age and DNO of the employees. This is the relation on which we are going to apply this operation, and this is the project operation. Then as a subscript we can specify the set of or the list of columns whose values need to be showed up in the result, and these list of columns should be separated by commas. It says that project from employee table or relation the column values name, age and DNO. This is called as projection operation. We can apply the expressions. One important thing to be noted is we can apply the expressions in sequence or we can nest them in a single expression. For instance, if we want to know the name and age of the employees who belong to department number 5, sometimes the simple queries may involve only one operation and some complex queries may involve more than one operation. And in this example, the previous queries, that is whatever we have seen in the previous slide, they involve only one operation. The first one involved only select operation, second one involved only the projection operation. But here in this case we need to find out the name and age of employees who are working with department number 5, and here it requires two operations. First, I should find out all the employee tuples where the value under the column DNO is equals to 5. That gives me the employee information for those who are working with department number 5. And then I need to project only on two columns, that is name and age. I can write this complex query at one shot using only single algebraic expression, nested expression, or I can separate them like this, what I have given in the bottom. First we will see how can we write the nested query. Employee relation, first apply the select operation where the select condition is DNO is equals to 5, and this expression, the first expression, will give you the result. The result of a relational algebraic expression or operation is also another relation. Now let us assume that the result of this is a temporary relation, and then that contains only the tuples from employees where the DNO is equals to 5. On the temporary relation, again we are applying the second operation, that is projection operation, wherein I am projecting only on the name and age. From the result of the first operation, I will project only on name and age, and that is going to be my final result. The above expression selects name and age of employees working with department number 5. The above query can be written as follows. I can split them. First, I write first expression. Series of or sequence of operations can be specified. First, on employee, I am applying the select operation where the select condition is going to be DNO is equals to 5, and the whatever is the result, I am temporarily storing it in the relation called as R1. And this concept is similar to that of what we see in the arithmetic operations. For example, I can write it as like this, B plus C, something like this at one shot, or otherwise I can say that B plus C, which can be stored in some variable x, and then finally I can suppose if it is y, something like this, I can say that y is equals to a into x. Yeah, both are same. It is, I am nesting the operations, I am writing one single expression, and whereas here it is split into two operations. Similarly, here also in relational algebra, we can write it at one shot, or we can split them into two different operations as a sequence of operations. According to this, what is the meaning? First, I will be applying selection operation on employee table. I will get a temporary relation, and what is the degree or arity of the, suppose if I have employee table where it has employee ID, name and age. Now tell me what is the degree of employee table. The degree or arity of the relation indicates the number of columns available with the relation. For the original relation EMP, the degree or arity is going to be 3, and then what I am doing is I am selecting only few tuples into R1. I am not cutting on the number of columns, so that is why the degree or arity of R1 is also 3. But the number of tuples may be less than what we have in EMP or same as what we have in EMP relation. And on this R1, which is a temporary relation, which is the result of applying selection operation, I am applying the projection operation wherein I will be projecting on name and age. And here, since I am interested only in name and age columns, now the final result is stored in R2 according to this expression. And what is the degree or arity of R2? It is going to be 2, because only 2 columns are showed up in the result. R1 and R2 are the names given to intermediate results. That's why whenever I apply some operation, the intermediate results are generated. If you wish, you can give some name to the temporary relation and use the temporary relation again in some other algebraic expression as if it is a normal relation. That is the advantage. Next, we will see union operation, which is a set theoretic operation. If two relations R1 and R2 are compatible, we call it as union compatible. Then we can apply or merge them by union operation, or we can apply difference operation, or we can apply the intersection operation. When we say that two relations are compatible, union compatible, if they have same number of columns for each tuple and the domain of each column is same. Suppose, for example, if I have a table called as employee, which has employee ID, employee name and then age, and wherein it is going to be an integer and it is a string type and then it is an integer type, and then if I have some other table or relation called as worker, and which has the name and department number, and this is string and this is going to be the integer, then in this case these two relations, that is employee and worker relations, they are not union compatible, because first point, the number of columns or attributes should match. It is not matching. Here in employee table we have 3 attributes, whereas here we have only 2 attributes. That is, the first condition itself has failed. Otherwise, let us assume that if it is not the case, then let us assume that I have one other relation whose name is worker, and it has the worker number and then the name and the age. In this case, what is happening? Let us assume that the worker number is equals to alphanumeric, and then this is a string, and this is a string, and this is integer. Though the number of columns are matching here, we have 3 columns here, 3 columns here, still I cannot say that they are union compatible, because the number of columns is same, but if you look at the domain of each of the column, then it is different. The first column or first attribute in EMP table, it is integer, but whereas here in worker it is going to be a string. So that's why the domain is not matching. Then I cannot say that it is union compatible. For 2 relations R1 and R2 to be called as union compatible, the number of columns should match. At the same time, the domain of each column should also match in the same order. They should be in the same order, but the name of the columns can be different. Then I can say that they are union compatible. To apply the union operation, intersection operation, and then difference operation, they need to be union compatible. Otherwise, I cannot apply these set theoretic operations on those relations. And why I am able to apply these set theoretic operations? Because a relation can be seen as a set of tuples. That's why I am able to apply these set theoretic operations on the relations. Now, R1 and R2, what is the meaning? Now, if you have a relation R1 and then R2, and then when I apply union, then the result will have, suppose if I have R1 union R2 and the result is stored in X, X will contain the tuples from both R1 as well as R2, but the duplicate tuples are automatically eliminated in this process. The second one is intersection, that is R1 and R2, intersection R2, meaning that the tuples which are commonly seen, which are seen both in R1 as well as R2, are available in the result. Only equivalent tuples from R1 and R2 are selected. And then if you look at the operation minus, that is the difference operation, R1 minus R2 means only tuples which are available in R1 and then which are not seen in R2 are seen in the result. And it is not commutative. That means union operation and then intersection operation, they are commutative. That means R1 intersection R2 or R2 intersection R1, both are same. Similarly, for union also it is same, but for difference, R1 minus R2 is different from R2 minus R1. That is why R1 minus R2 is not same as R2 minus R1. This is a very, very important point to be noted. And then let us have a look at this cross product or the Cartesian product. If we have 2 relations R1 and R2, and how many columns are there? Let us assume that this is column 1 and then column 2, and then this is column 1 and then column 2. To apply this Cartesian product, the relations need not be union compatible. That means the number of columns need not match, it can be different. And each of the relations R1 and R2, they have 3 rows or 3 tuples in each of the relation. Number of columns are 2. That is why the degree of R1 is going to be 2 and then degree of R2 is going to be 2. If I apply the Cartesian product operation, what will happen is the tuple 1 will be joined with all the 3 tuples in relation 2. That is why I have A11, A12 and then B11, B12. This is joined with this. Then A11 is now joined with this tuple A11, A12, B21 and then B22. And then same first tuple is being joined with the third tuple in the second relation. So for tuple 1 in or relation 1, I have 3 combinations or I have 3 joined tuples in the result. Similarly, for tuple 2 in R1, I have 3 joined tuples, and then for tuple 3 I have 3. So total, how many tuples will be there in the resultant relation? It will contain, since there are 3 rows here and then 3 rows in the R2, so 3 into 3 it is going to be 9. There will be 9 tuples in the resultant relation. That is going to be the characteristic of this Cartesian product. How many columns will appear in the result? Because the degree of R1 is going to be 2 and then degree of R2 is going to be 2. So then it will be 2 columns from here plus 2 columns from the other relation. Total there will be 4 columns will show up in the result. Suppose if I have a relation R and which has 3 columns and then 4 rows, and then I have, let us assume that I have one more relation S which has 2 columns and then 3 rows. Now how can we decide how many number of columns will be there in the result? If I apply R Cartesian product S, there will be 3 plus 2, 5 number of columns will be there in the result. And how many rows will be there? Since there are 5 rows here and then 3 rows here, 5 into 3, in total there will be 15 number of rows in the result. That is the characteristic of the Cartesian product. Then let us have a look at the renaming operator. Sometimes it is required while specifying the queries to rename the names of some queries, relations, or rename the attributes of some relations. And the operator used, the symbol used for this is the row, and then the meaning of this is, let us assume that there is a relation R with A, B and C as the attributes. The meaning of this expression is, since I am applying this renaming operator, the R will be renamed to S, and then the attribute names will also be changed, and the new attribute names are going to be B1, B2 and then B3. So this is the renaming operator, and sometimes we can rename only the column names, or sometimes we may rename only the relation or table name, sometimes both. Let us take a look at these examples with respect to renaming. Let us assume that there is a relation EMP which has original name is EMP and the original attribute names are EID, ENAME and age. Suppose if I wish to rename the relation name as worker and then leave the names of the attributes as it is, I can write a statement, I can specify it like this. EMP is the original relation, and here the row symbol I am using, and then worker. That means I am not touching the names, I am not trying to modify or change the names of the relation attributes, rather I am just changing the name of the relation. The result is going to be like this. The name is now worker and the attribute names are same, employee ID, employee name and then age. And if I wish to change the name of the relation as well as name of the attributes, I can specify it like this. Employee is the original relation name, and I would like to change it to worker, and the first attribute would be E number, second will become title, and third one I would like to like it to be wage or W age, that is worker's age, W age. The result of this is going to be like this. The attribute names as well as the relation name have changed after applying this renaming statement. Then if I want to change only the attribute names, I can do that. Here I don't want to change the name of the relation. Now I would like to change only the attribute names of this original relation EMP. For this original relation EMP, I am specifying that the attribute names need to be changed. Then the name of the relation is same, only the attribute names have changed. Suppose I don't want to change the name of the relation. At the same time, I am also not interested in changing the names of other two attributes, that is ENAME and then age of this employee relation should not be changed. I would like to change the first attribute name from EID to E number. Then I can specify it like this. Employee is the relation, and 1 indicates that the attribute 1 need to be changed to E number. That means whatever is the old name, that will be now modified or replaced with the new name ENO. This is how we can use the renaming operation. Next very important operation is the division operator, and used when we want to check the meeting of some criteria. Let R is a relation which has A and B as the attributes, and S is another relation where A is the attribute. let us assume that the domain of this A attribute and then this attribute in these relations are same, and if I apply the division operator R divided by S and the result is T, and then in T you will find only one attribute, that is B. That means R contains A and B and then S contains only A. So, the result T will contain this set minus this set, and that will be the attributes that will show up in the result, that is T. It selects all the values for B column in R which contains all values under A in S. Hence, the number of columns in T is only B, that is only one column will be there according to this example. Let us have a look at one more example that gives us clear idea about how this division operator works. Let us assume that I have employee project relation which has two attributes, that is employee ID and then P number. That means this indicates what employee is working on what project. The rule says that one employee can work with more than one project and same project can have more than one employee. So, that is why 101 employee ID is working with 3 projects and 102 is working with only one project, that is P2, and 103 is on one project, 104 is working on 2 projects and 105 is working on project P3. And now I want to find out, I know that the very good projects in the company are P1 and P3, they are high priority projects, and that is available in the table good project, good underscore project. There is only one attribute, that is P number, and then this P number domain and this PNO is going to be same. Let us assume like that. And what are the good projects available? What are the high priority projects available in the company? That is P1 and P3. Now, having this kind of information available, now I would like to find out who are the employees who are working on all the high priority projects or good projects. Then in that case, I need to go to the employee project table and then figure out all the employees who are working with the listed projects that are available in the other table, that is good project table. That means for each employee I will check whether he is working on P1 and P3 or not. If he is working on these two, then his name or his name will appear, or his employee ID will appear in the result. That should be the requirement. Then in that case I can use this division operator. So, if I say employee project divided by good projects, meaning that what? Now I will go to employee project and then I will check who are the employees who are working on all the project listed in the other relation, that is good projects relation. And if you carefully observe, 101 is working on P1 and P3, 102 is not there because he is not at all working on P3, 103 is also not there because he is not working on P3, and 104 of course he is working on both P1 and P3, and then 105 will not be there in the result because he works on only one project, one good project, that is P3. Now, according to this, who are all the employees who work on all the good projects that are listed in the good underscore project table? That is nothing but 101 and then 104. So, this is how we can make use of this division operator when you want to find out something which satisfies the criteria that is specified in some relation. Okay. Now, how can I find out? So, that is the result of this operation is stored in R, and then how can I find out how many columns or attributes will be there in resultant relation? So, now if you look at this employee underscore project, how many attributes are there? It contains employee ID and then P number. How many attributes are there in good projects? It is only one, that is P number. Now, the number of columns or the list of columns that are seen in the resultant relation, it is going to be this set minus this set. So, that is why you will find only employee ID in the resultant relation. Okay. Now, let us look into join operators. This is the symbol for join operator, and then it is used to join tuples from different tables based on some condition, and result is also a new tuple with a different degree or arity. Suppose, let us assume that I have a department table and then employee table, and then in department table I have a column or attribute called manager SSN, this one, and which is a foreign key pointing to SSN of the employee table. Now, I would like to find out, join the tuples which are spread across the department table and then employee table based on the condition that the manager SSN in department table tuple should match with the SSN of the employee tuple in employee table. So this is how I can specify. This is relation 1. The join operator is a binary operator. That means it requires 2 operands. The division operator is also a binary operator, but the selection and projection operations are unary operators. And then I have the second relation, that is R2. I apply the join condition, join operator. What should be the join condition? The manager SSN value in a department table should be equal to same as the value of SSN in employee table. Only such kind of tuple should be joined and then made available in the result. The result is, in this case, it is going to be D. Now let us assume that if I have 3 columns in department table and then 5 columns in employee table, then the result will contain 3 plus 5, that is 8. The degree or arity of the result is going to be 8. Let us have a look at this example. Okay, I have department relation with dnum and dname, location, and then manager SSN, which is a foreign key pointing to SSN of the employee table, which indicates who is the manager of the given department. Then in employee table I have SSN, ename, and then age. If I specify, if I write this query, department joined with employee where manager SSN is equals to SSN, the result will contain the all the tuples, or sorry, all the attributes from department and all the attributes from employee table. So that's why 4 plus 3, in total there will be 7 columns. That's why the degree or arity of the resultant relation is going to be 7. Now there are so many kinds of joins available. Theta join, the joining operation on some condition with comparison that involves any of these operators: equals, greater than, less than or equal, greater than or equal, not equals. Any of these operators is, comparison operators is involved in the join condition, it is called as a theta join. Then equi-join is a special type of join where the join condition is always equals, it is always equals. In the previous example whatever we have seen, it is a equi-join because the selection of, the join operator has been specified with condition which involves only the equals operator. And then we have a join called as natural join, is an equi-join on attributes in R and S having the same name. That means, suppose if 2 relations have same name, same columns with same name, then we can apply this natural join. So for example, if I have employee table with employee ID, employee name, and then DNO, and then if I have department table with DNO, dnum and then dname, now I cannot join the tuples which are spread across employee and then department table using natural join, because there is no commonality with the names of the columns. No 2 columns in these tables have same name, so that's why it is not possible. Then I can apply equi-join. I can say that employee joined with department where DNO in employee is equals to D number in the department. This equi-join is possible, but when this natural join is possible, when the name of this is DNO, that means this is a foreign key which is pointing to this, and then name of this and then this, both are same. That means if at least one column in one relation R and one column in relation S, they have same name, then I can apply, or then I can write a natural join statement. In this, how to specify the natural join? I can say that employee natural join department. I don't have to specify, this is the symbol used there, star symbol. I don't have to specify any join condition, because by default it is understood that the joining is on the columns which have common name across these 2 tables. So that's why by default it will look for the same titled columns or the columns with the same name, and the tuples across these 2 tables will be joined based on the equality of that particular column value. The joining is on common attribute with same name, the department name in the, for example, let us have a look at this. This is one relation, this is another relation, this is employee relation, and this is department relation, name, employee ID, DEPT name, and here the DEPT name and then manager. Now, if I simply say employee naturally joined with department, it is by default on the department name, because this is the common attribute or column available in both the relations. So, that is why it will join the tuples across the these two tables on the equality of the value for these two columns, and then it will generate the result. So, that is why this will join with this, and this will join with this, and this can join with this, and then this will join with this. So, that is why Harry, that means now if you look at the degree or arity, it is because in the result you will find both columns, because these two columns are going to be same, they are with the same title or column name. So, that is why one of them will be knocked out, only one among these duplicate columns will appear in the result. So, that is why here you have 3 columns, here I have 2 columns, but if you look at the result, it contains 3 from first one and then only 1 column from the second one, because the department name is redundant. So, that is why it is eliminated or removed. You see only 1 column under this department name, and this is how the natural join operation works. And we have inner join and outer joins. An inner join only combines the tuples from R and S if they meet the condition. The tuples that do not meet the condition are not showed in the final result. Okay. So, that is called as inner join. For example, if I have employee table, and then if I have department table, and then if I have employee ID, and then employee name, and then age, and then here and D number in the employee table, and then D number and then department name in the other table, and if you have some 101 and 102, and then name is A and B, and age is 28 and then 30, he is working with department number 10 and working with department number 20. And let us assume that in the department table I have only one tuple, that is I have only one department whose name is marketing. Now, if you say that employee joined with department where D number from employee is equal to D number from department, then there is the D number value is same for these two rows in these two tables. So, these two are joined, but there is no matching tuple for this tuple in employee table, that is for 102 employee, there is no matching tuple in the other relation, that is department relation. So, that is why that will not show up in the result. If you look at the result, only this much will appear, that is 101 A 28 10 10 and then marketing. The other tuple which is part of this employee relation is not showing up in the result, because it has no matching tuple in the other relation, joint relation. So, that is why it will not it is not seen in the result. This is called as inner join. That is only those tuples from both the tables which have corresponding matching tuples will show up in the result. The other tuples will be eliminated from the result. This is called as inner join. But in specific conditions, we may need to see the tuples from either one of the relations or both the relations to appear in the result, independent of whether they have a matching tuple in the other relation or not. So, that may be the case. In that case, we will be using outer joins. An outer join displays the tuples of one of the relations even if there is no match for the tuple in the other relation. We have left outer join, the symbol is this one, and we have right outer join, the symbol is this one, and we have full outer join where the symbol used is this. This is left outer join, because if you take R and S relations, if I apply a join condition, I would like to see all the tuples from R irrespective of whether those tuples have matching tuple in S or not. This is called as left outer join. And then if the situation is such that I have R and S which are joined using a join operation, I would like to see all the tuples from S, then it is called as right outer join, because this is the right side relation. And in some cases I have R and S, I join them using join operator, but I would like to see all the tuples from R and S in the result independent of their matching tuples in the other relations. This is called as full outer join. Let us try to understand this concept using some example. Let us assume that I have a relation called employee which has employee ID, employee name, age and D number, I have another relation DNUM department which has DNUM, that is department number, and then DNAME. Primary key is this one, here the primary key is employee ID. And DNO here in employee table is a foreign key which refers to DNUM of the department table. And let us assume these tuples in each of the relations. In employee table I have 5 tuples, in a department table I have 3 tuples. There are 3 departments, department number 10 marketing, 20 accounts, and then 30 production. If I perform the normal join here, then this will be joined with this. If I am performing a normal join operator between these 2 tables where DNO is equals to DNUM in the department table, that is, it can be written like this: employee joined with department where DNO is equals to DNUM. Then in this case what is going to happen? This will be, because for this tuple in employee table there is a corresponding matching tuple in the other relation. For this also you have a matching tuple, for this you have a matching tuple, and of course for 40 department employee 135 who is working with 40, but there is no department 40 in the department table. So that is why there is no corresponding matching tuple for this tuple in the employee table. So that is why that will not show up in the result. Similarly, for employee 156 also there is no corresponding matching tuple, that is why it will not show up in the result. Hence, in the result, if I simply apply the normal joining on the join condition DNO is equals to DNUM, it will show up only 3 tuples from here and the corresponding information from the matching tuple from department table. But I have a specific requirement wherein I would like to see all the tuples from employee table independent of whether they have a matching tuple or corresponding matching tuple in the department table or not. In that case, I can use a left outer join because the employee is on the left hand side of the join operator. I can write it like this: employee left outer joined with the department where DNO is equals to DNUM. Now, in that case what will happen? The corresponding tuples are only these things. Okay, that is why 101 Raj, 28 department number 10, and here 10. If you look at the degree or rarity, we have 4 columns here, 2 columns here, total 6 columns will be there in the result, and the name of the department is going to be marketing. For 110 also there is no problem because there is a corresponding tuple, he works with marketing department, and 128 department number 20 there is no problem. And then as far as 135 is concerned, there is no matching tuple in the department table. That is why the information about the employee is displayed, because that is my requirement. That is why I have gone for the left outer join. But as far as the attribute values for the other relation will not be available because there is no corresponding matching tuple in the other relation, and under those columns for this particular tuple it will be padded with null. Sometimes it could be it will be null. Let us assume that it will contain null values, something like this. For similarly for employee ID 156 also, and he works with department number 50 and there is no corresponding department in the department table, that is why this will also be padded with null values. This is called as the left outer join. And sometimes we may need to have right outer join. Then in that case, that is, my requirement is I join employee and department, but I would like to see all the department information independent of whether the department has a corresponding employee in the employee table or not. If you look at the department table here, it is evident that I have 3 departments here, but with the department number 30, which is a production department, there is no employee working with that particular department. And according to my requirement, I can write this right outer join. Now the employee 101 working with 10, there is no problem. I have information regarding corresponding department, and 110 is also no problem, and 128 is also no problem. But I want to display the information about department number 30, though it has no corresponding matching tuple in the employee table. So that is why I display the information about department number 30, that is department ID and the name of the department, that is production. Since there is no matching tuple on the employee side, that is why the values under the columns of employee relation will be padded with null. So that is why I have null values here. So this is called as the right outer join. And sometimes what happens is I may need to see the information in both the relations independent of their corresponding matching tuples in the other relations. So in that case I can go for full outer join. If I say that employee, full outer join, this is the symbol for full outer join, department, meaning that all the tuples of employee will also show up in the result, and all the tuples from department will also show up in the result. This is the concept of outer join. We have left outer join, we have right outer join, and then full outer join. If I simply say join, it is nothing but inner join, because according to the inner join concept, only those tuples which have matching tuples in the corresponding tables will show up in the result. It is inner join. That means if I simply say a join, it is nothing but inner join. Then we have additional relational operations like aggregate functions, sum, average, max, minimum, and count. What is the basic characteristic of aggregate function is, these aggregate functions can be applied on some set of values and or some list of values, and when you apply this aggregate operation, always independent of the number of elements available in the list, it is going to give you back only one single value. Suppose if you assume that there are 1000 values, integers in a list, and then if you apply sum, it will return you back only one value, and then average also will return you one value. Similarly, maximum, minimum will also return you only single value, and then a count is a very special kind of aggregate function which will always return you the number of elements in the set, number of elements in the given sequence or the list, not set. Okay. And we have grouping operation, which is a very important facility in relational algebra. The tuples of a relation are first grouped by value of some attribute, and then aggregate functions can be applied to individual groups. The symbol used is, and please make a small correction, this is not the symbol used, actually this is the symbol that need to be used for this grouping operation, and this is called as script F. This is the symbol used, and that means if you group the tuples in a relation based on some value of an attribute, now it will form groups, and then if you apply some aggregate operations, they will be applied on individual groups, not on the entire relation. Suppose let us assume that I have an employee table which has employee ID, employee name, age, and then department number. These are the 4 columns, and then I want to, let us assume that there are approximately some 1000 employees are there, and then 1000 employees information is stored in this employee table. Now I would like to find out how many employees are there in each group. Let us assume that there are 3 departments of each department. Let us assume that there are 3 departments, department number 10, 20 and 30. Now I would like to display the department number and then number of employees working in that particular department. In that specific case, I can always use the group by operation. I will take this employee relation, I will group the tuples based on DNO, then all same, the tuples which have same value under the DNO column will be put into one single group. Now we can imagine how many groups can be formed, because there are 3 departments, distinct departments available, and all available 1000 employees will be put into these 3 departments. That is, there will be 3 groups formed. Now how can I count how many employees are there in each group? By applying the count operation on the value of on the column SSN. Okay, that is, here it is SSN is not there, of course it need to be EID, and then if I count how many distinct values are there in each group, then I can find out how many employees are working with each group. In total there will be 3 groups, group 1, group 2, and then each group will have certain number of tuples which is always equivalent to number of employees working with the group, and then if you count on employee ID, that is the distinct values, it will always give you the number of tuples in that each group. So similarly, you assume that 600 with the department number 10, 200 with the department number 20 and 200 with the department number 30, and if you apply this grouping operation, what will be the result, the shape of the result? When you apply grouping operation, the grouping attributes will show up in the result, hence the D number is showing up in the result. At the same time, for each aggregate operation you apply or aggregate function you apply, there will be a column. Since I am applying count, it is going to be count SSN, and this you can store it in a temporary relation, and then of course if you wish you can give different names or new names to these columns. So this is how the result of a grouping operation appears. For each grouping attribute there will be a column, and for each aggregate function there will be a column in the result. So now the employee table, the tuples will be grouped based on the value of department number attribute. Since the department number attribute value could be either 10 or 20 or 30, it will form 3 groups. After forming groups, it will apply the aggregate function. That is why when you are applying aggregate functions, first you need to apply grouping, then you need to apply the aggregate function. The aggregate operations will be performed on the individual groups rather than on the entire table. So the count operation is going to count how many tuples are there in each of the groups. That is equivalent to the number of employees working with each of the group. And if you look at the database schema, relational database schema for company database, I have employee table, department location table, project table, works on table, and then dependent table. Now let us try to form some queries in relational algebra to get some extract some data from the database. The first requirement is, that means whatever data retrieval requirements I am going to specify, it is going to be on the previous database schema, on this company database schema. The first requirement is, I would like to get the list of employee IDs who have no dependents. When this kind of requirement is given, first we need to clearly understand what is the requirement, or what is the meaning of the what should be the database and what should be the relations that need to be accessed to get the data from the database. That means we should clearly understand what need to be extracted from the database, and then we need to figure out what relations need to be accessed, and then we need to figure out or decide upon the operations that need to be applied or performed on these relations to get or extract the data from the database. The first, that is, we are going to write all these queries or data retrieval requests in relational algebra on this database schema, that is company database schema. The first requirement is, get the list of employee IDs who have no dependents. That is, I need only the employee IDs of those employees who are not having any dependent. How can I get that? The dependent, the information is available in dependent table, the employee information is available in employee table. The simple thing is, if I can get the set of employee IDs, and if I can get the set of employee IDs who have dependents, at least one dependent, and then if I perform a minus operation on this, then I will get the employee IDs who are not having, for the employees who are not having any dependent. So that is why first get the list of employee IDs, go to employee table, apply projection operation, project on SSN, and store the result in R1. How many columns are there in R1? Since I am going to project on SSN, the degree or RET of this relation is going to be 1. Similarly, go to dependent table and project on ESSN, and then store it in R2. You will have only one column. Now SSN and then ESSN, though the names of the columns are different, the domain is same. So that is why the R1 and R2 relations, which are temporary relations, are union compatible. Now I can perform R1 minus R2. What is there in R1? All list of all employee IDs. What is there in R2? List of all employee IDs who have at least one dependent. So this will give me the set of employee IDs who have no dependents. So that is why first clearly understand the requirement, then figure out what relations from the database need to be accessed, then decide upon what operations need to be performed, and then in what order. That is very, very important. The next one is, get the list of employee IDs who have more than 2 dependents. Here I need to, it is a complex query, I need to apply the grouping operation. Go to dependent table. If an employee has at least one dependent, his employee ID will appear in the dependent table, his entry will be there in the dependent table. So that is why go to dependent table, group the tuples in dependent table based on the ESSN. If the employee, for each employee there will be a group. If the employee 101, if he has 2 dependents, then there will be 2 tuples for this employee. If 102 has only 1 dependent, there will be 1 tuple, and if 103 has 3 dependents, then it will have 3 tuples or 3 rows in the group. and after grouping then you apply the count operation on the dependent names. For a given employee, the dependent names cannot be same. So that's why you apply the count operation to count how many dependents are there in each group. Okay, so that's why what will be the result of this first operation? Go to dependent table and then group it based on ESSN and then count the dependent name. So you will have ESSN and the second column will be count dependent name. Two columns will be there for the result. This is the R1. For this R1, you check whether the count number of dependents is greater than 2 or not. 2 or not. Then for such tuples, you project on the ESSN. That is going to be the result. So this is first we apply the grouping operation, then we apply the aggregate function count, then in the next step we will see how many dependents are there in each group. If the number of tuples in each group is greater than 2, it indicates that he has more than 2 dependents. Then for such tuples we project only on employee SSN and then that will be the result of this query. The third requirement is get the list of projects controlled by department with name accounts. Go to first I need to find out the departments who are having the name account, the department ID whose name is account. So I will go to this department table and then select on the tuples where the department name is equals to account. Then I will be storing in R1. Then that temporary relation R1. Now if I have 3 columns or 3 attributes, suppose if you go back to that database, company database, how many columns or attributes are there in department? There are 4 columns. So if I am selecting based on some condition, how many columns, what will be the degree or rarity of this relation? It is going to be 4. That means I am selecting only few tuples where the name of the department is equals to account. I am not cutting down on the number of columns. So that's why the degree or arity of the relation R1, it is going to be same as the department table. Now that R1 I am joining with the project table and I will say that the joining condition is equals to dnum in project table is equals to dnumber in the department table, because in the project table I am storing the information about the controlling department in the form of dnum, which is a foreign key which is pointing to dnumber of the department table. Now so that's why I am joining R1 with the project table with this join condition, and after doing that I am projecting on p number and then p name. This will give me the project name and the name of project number for those projects which are controlled by accounts department. Next we have a requirement, get the list of employees or employee IDs who are working with all the projects in the company. And this is here I need to find out, I need to do this using the division operator. First I will figure out the employees and project numbers, that is employee SSN. Let us assume that I have a relation R1 which has this schema, employee SSN and PNO, project number. How can I get that? Go to works on table which stores the information about the employees and their projects. Go there and then project on the ESSN and then P number. Let us assume that this is R1. Similarly, go to R2 and then project on the P number. That will give you the list of all projects that are available in the company. Then if I want to figure out the employee SSN who are working with all the projects, means what? Suppose if I assume that there are 3 projects, P1 and P2 and P3, and then if there are employees and their projects, then if the employee ID which is satisfying all these projects, how can I get that? Simply apply R1 divided by R2, that will give you the list of ESSN, that is the employee IDs who are working with all the projects available in the company. A solid example how the division operator works we have seen already in the previous discussion. Next, find the projects controlled by departments located in Mumbai. That means what? In project table I have the department number dnum, which is a foreign key pointing to the controlling department. But first I need to figure out the D numbers or the numbers of the department numbers which are located in Mumbai. So I go to department locations table and then select on those tuples where D location is equals to Mumbai, and then project on D number. And R1 will contain now only one column, that is D number, and these D numbers will be, suppose 10 and 20 are there, meaning that the department number 10 and then department 20 are located in Mumbai. Now I need to figure out which are the projects that are controlled by department number 10 and 20. That gives me the information about the projects which are controlled by the departments which are located in Mumbai. So I need to join the temporary relation R1, which contains department numbers of those departments which are located in Mumbai, with the project relation. And what is the join condition? D num in the project is equal to D number in R1. And once you do that, then you figure out, you project on the P number and then project name from this result, and then ultimately you will get the final result, which will contain the project number and then project names for those projects which are controlled by departments which are located in Mumbai. So this is how we can specify the data retrieval requests, which we call them as queries, using relation algebraic expressions. The relation algebraic expressions, the result of each relation operation or relation algebraic expression is also another relation. And this is a formal query language for relational data model, because this relational algebra has a strong mathematical background. Only experts can pose their queries using relational algebra, and that's why, to facilitate easy and then simple data retrieval request specification, the relational data model vendors, that is all commercial data management systems in relational model, they support SQL, which is a commercial query language for relational data model. And whereas the relational algebra and then relational calculus, they are formal query languages which are based on strong mathematical background. Now let us have a look at tuple relational calculus. Relational calculus is one of the formal query languages for relational model, where we write one declarative expression to specify a retrieval request, and hence there is no description of how to evaluate the query. A calculus expression specifies what is to be extracted or retrieved rather than how it need to be done. Hence relational calculus is non-procedural language. This is very important point. And whereas the relational algebra, what we have discussed so far, is a procedural language. The difference is, in relational calculus I am not specifying what operations need to be performed and then in what sequence it need to be performed. Just I specify what need to be extracted from the database. That's why the relational calculus, which is a formal query language, is called as a declarative query language. And whereas relational algebra is a procedural query language, because in relational algebra, what we have seen in the previous case, I decide upon what need to be extracted from the database. To achieve that, I will be writing a sequence of relational algebraic operations, okay, in a particular sequence to get or extract the required data. So that's why it is called as procedural. I am specifying what operations in what sequence and how the data need to be extracted from the database. That I am specifying in relational algebra. That's why it is procedural. Whereas the relational calculus, no such information is available. Rather, I just specify what need to be extracted, not how. That's why it is called as a non-procedural formal query language for relational model. Any expression for data retrieval written in relational algebra can also be written in relational calculus and vice versa. Hence, as far as the expressive power of relational calculus and algebra is concerned, both are going to be same, because whatever I can write using algebra, I can also specify the same thing using relational calculus. The expression power is same for both these formal query languages. The tuple relational calculus is based on specifying a number of tuple variables. It is a calculus, meaning computation, which involves variables wherein the tuples of relations themselves, they become variables. Hence it is called as the tuple relational calculus. The calculus that involves tuples as variables, hence it is tuple relational calculus. Each tuple variable usually ranges over a particular database relation. Normally any tuple you take, that belongs to a relation. Variables can take values of individual tuples. So hence, if it is a integer variable x, what it can take? It can take any integer value. Similarly, if I had declared a tuple variable t, what can be stored in this? A tuple can be stored in the tuple variable of specific type. A simple relational calculus query is in the form it starts with a curly brace and always ends with a curly brace, and in between T such that the condition, that means show me or get me all the tuples where the tuple is satisfying the condition specified here in this formula. T is a tuple variable, that means at each iteration some tuple will be assigned to T, which is a tuple variable, and then the conditions that are specified in the formula will be applied onto the tuple values, and then if it is meeting the condition, then only such tuples will appear in the result. Condition T is a conditional expression involving the tuple T. Result is a set of all tuples that satisfy the conditions specified in condition T. Let us have a look at some small example. Find all employees. Let us consider the same database schema, that is company database schema. I would like to find out all employees whose salary is greater than 50,000. T, employee T, and T dot salary is greater than 50,000. That means T is a tuple variable, and this tuple variable, what is the type of this tuple variable? The type should be employee. That means these tuples will range over the employee relation, and each time I assign a tuple from the employee table to T, and I will check for this value for a given column. That is, T dot salary means that is how I can refer to the value of the salary in the relational schema. So that is why T dot salary means the salary attribute of the tuple T, and if the value is greater than 50, such tuple will appear in the result. Suppose if I have employee table, then if I have employee ID and then employee name and then salary, if I have 101, 102, 103, names are ABC, and if it is 60K, 30K and then 40K, that is the salary, and first this is the tuple, because in the formula it is clearly specified that the tuple variable T ranges over the employee relation. So that is why in the first iteration the first tuple will be assigned to this tuple variable. T is a tuple variable, hence a valid tuple can be assigned to that tuple variable. So the first tuple is assigned to T, then I will go to T dot, now this is referred by T. So T dot sal is equals to 60K, this satisfies the condition, hence the first tuple of the relation employee 101 A 60K will appear in the result. In the next iteration the second tuple is assigned to T, and again it will check T dot salary. Now T dot salary is equals to 30K, but it is not greater than 50,000, hence this will not show up in the result. In the third instance, the third tuple will be applied assigned to the tuple variable T. Again the condition is tested, it satisfies, sorry, it is not going to satisfy, hence that will not appear in the result. Hence in the result only one tuple is there according to this given example. It selects all the tuples from employee such that for each tuple selected the salary value is going to be greater than 50,000. The expression EMP T specifies from where the tuple T must be chosen. It is called as, I am binding this tuple T to the employee relation. That means the tuple variable T ranges, the tuples will range over the employee relation, hence the EMP relation in this case is called as a ranging relation or range relation. The above query retrieves all attributes. In this specific case what happens, it is only a selection operation. I am checking for a condition, if it is satisfied all the attributes of that particular tuple will show up in the result. In some cases we may need to apply the universal and then existential quantifier, and then existential quantifier, and some cases we do not have to see, we may not want to see all the attributes in the result. In such case, suppose let us assume that to retrieve the name and age of all the employees who are working with research department, how can I write a query in tuple relational calculus? T that should range over employee table, and there exists another tuple variable D which is ranging over the department table, and D dot name, that is the name of the department, is equals to research, and D dot DNO, that is for the tuple D, if the DNO is equals to T dot DNO, T is what? T is ranging over employee tuple. For such tuples you give me the name and age of the employees, and here you can appreciate the use of the quantifiers. We can use existential quantifier and then universal quantifiers. And if a variable is attached or associated with an existential or universal quantifier, it is called as a bound variable. Otherwise, it is called as a free variable. In this particular example, which is the tuple variable that is bound to some quantifier, the D is a tuple variable which is bound to the existential quantifier. Hence, D is a tuple variable which is bound, it is a bound variable, whereas T, this T which is not bound to, not associated with any quantifier, hence it is called as a free variable. Only free variables can appear in the result of a relational calculus expression. That is one important point to be noted. Then we have a notion called as safe relational calculus expression. It says that a safe relational calculus expression is one that always guarantees to yield a finite set of tuples in the result. For example, if you consider this T ranging over employee T, what is the condition? That T should not belong to employee. So, it should not range over employee, that is the meaning. That is, to get me all the tuples where T is not belonging to employee relation. So, it is unsafe because it is going to yield all the tuples in the universe that are not in employee relation. Hence, it is a unsafe relational calculus expression, which are in this case it is going to return you infinitely numerous number of tuples, that is all the tuples that are not belonging or that are not in employee relation. Hence, it is unsafe. An expression is safe if all values in its result are from the domain of the expression. So, they are called as the safe relational calculus expressions. Then we have one more important notion called as relational completeness. This notion is used to compare high level query languages. Any relational query language L is considered to be relationally complete if we can express in L, that is this query language, any query that is expressed in relational algebra or relational calculus. We know that the expression power of relational algebra and then relational calculus, which are formal query language for relational model, is going to be same. Suppose let us assume that I have proposed a query language for relational model whose name is L. When I can say that this query language L is relationally complete? When whatever query you can specify using relational calculus or relational algebra, if you can specify all those queries using your language L, then I can say that the language L is a relationally complete language. Otherwise, it is not relationally complete. For example, SQL is relationally complete. That means whatever queries you can specify in algebra or calculus, the same thing can be specified or written using SQL statements. That is why SQL is a relationally complete query language. This notion, this concept of relational completeness is used to compare the quality of high level query languages. Okay, in this session we discussed what is a query language and what do we mean by formal query languages for relational data model. We have relational calculus and then relational algebra, both are formal query languages which have very good mathematical background. And then we have discussed the basic concepts related to relational algebra and what are the various types of operations, that is set theoretic operations, and then relational operations we have seen. We have union, intersection, Cartesian product, difference, then we have seen selection, projection, division, join operators. We have also discussed about the concept of outer joins. Then we discussed about the grouping operator and then functions which are called as aggregate functions, which can be used in conjunction with grouping operator in relational algebra. Then we had a brief discussion about the relational calculus to see the basic structure or the basic format of a relational calculus expression. And we have also seen some examples with respect to the relational algebra, wherein we have considered the company relational database schema, and then we try to write or specify some data retrieval requests using relational algebra language, formal query language. Let us stop here. Thank you very much.